Hello everyone, I am Chuanxin Lan, an engineer from RCT, Chinese Academic of Science, and I want to introduce you AIBench Inference. Consider the diverse set of AI models, AI frameworks, and data types, which is the state of the art workers and extract several trained model which can represent the diverse driver set. Although the workload are comprehensive, the inference time is much slower than other processing time. Therefore, the benchmark cost is affordable based on those comprehensive workload behaviors. We propose a new workload characterization methodology, WPC, and propose a set of algorithm system and Characterization. We propose 3 representative inference model. This is our outline. AIBench Inference workloads also cover many different networks like CNN, ResNet, LSTM, and others. It also contains workloads for different data types, include text, image, audio, video, and 3D data. There are 19 representative AI tasks selected from 3 international servers, which are such energy, social network, and e-commerce. And their model, dataset, and the set of the art model are displayed in this table. We can find we have a lot of dataset and different model size. Next, I will introduce the benchmark affordability. We test 14 tasks on V100, and from this table, we can find in high accuracy promise the inference time is short for system, so it is affordable to test million tasks. Then I will introduce workload characterization. We first introduce the transitional methodology. Clone should perform a Microarchitecture-independent workload characterization of the scale-out workloads, and they clocked have a high front still is the inherent characteristic that place the scale-out workload into a distant workload class from the desktop, parallel, and transitional server workloads. Using medical characteristic-dependent workload characterization, host analyze 116 benchmarks from 6 benchmark suits. HPEC CPU 2000 MetaBench, MiBench, Ball-Informark, Ball Matrix workload, and Common Bench. The vector diagram representing the net key Microarchitecture-independent independent the tasked AI represent inherent behavior patterns. Box represent cluster and at rest include cluster representatives. So perform the RSA independent workload. Characterization for what's important intrinsic program. Characteristic relating to computation, memory, and control flow. The analysis is performed using a GIT computer that imitates RSA independence instructions. The figure is a comparison of 5 RSA independent metrics across SPEC benchmarks. Ordered by the area of the program, the low right point provides the legend and similar errors include more regularity in the metrics. Our experiments found that all these three kinds of methodology have a limitation for modern scale-out workloads. For medical characteristic independence and medical characteristic dependent method, we perform the experiments on a scale-out workload with C, Java, Python, Hadoop, TensorFlow, MPI, and a transitional workload with a C implementation. We found that have a higher front end still is not the inherent characteristic of the scale-out workloads. For the RSA independent method, we found that the instruction characterizes similarly between two workloads. Implementation at the IR level does not group their instruction behavior characteristic with the similar at the one at the other two levels. In order to achieve the diversity of workload behaviors, AIBench Inference adopts a new workload named the whole picture workload. Characterization method WPC solves the limitation we discussed above. We present a whole picture workload method and the tool. WPC integrated Microarchitecture-dependent, Microarchitecture-independent, and RSA independent methodologies. It performs a whole picture analysis on perform data across intermediate representation IR, RSA, and microarchitecture to sum up the inherent workload, characteristic, and understanding the reason behind the neighbors. We collect the IR stream with the LLVM tool, feed them to a logical processor model with the no control and pipeline model. We collect the pin stream with the pin tool, feed them to a perfect processor model with the no pin line model. But a perfect control model with always complete all memory reference in a single score. We use a performance monitoring unit tool like perform to obtain microarchitecture metrics on specific performance. The IR level analysis is behind the runtime environment and OS and RSA independence, where the RSA level analysis is behavior is beyond the OS and Microarchitecture independence. The Microarchitecture level analysis is afforded by the OS and the Microarchitecture independent. We conduct WPC on short with C, Java, Python, Hadoop, Java-based, TensorFlow, Python-based, MPI, C-based, implementation, and implementation with the C implementation. Short and matrix implementation represent a typical scale-out and traditional workload. We have the following presentation first at the Microarchitecture level. We observe that source different implementation led to varied L1 and the implementation using a high productivity language like Java, Python, or a framework with a high productivity language like Hadoop. TensorFlow had higher front-end store than that of C. The traditional workloads. Second, the RSA level rules keep consistent trends with that of the Microarchitecture level. Third, each sort implementation instruction entry is similar to the IR level, and the gap is not more than 1.5 times the close instruction interpret implies that each sort implementation instruction locally is similar when including the after of the runtime environment and the OS. This is instruction at the IR level with respect to the other two levels. POP used to investigate what makes a difference. We speculate it is a specific optimization that makes a difference. We try training of Java and Python's completion option and change to an interpreter model at the Microarchitecture level. The third Java and the third Python MPKI is reduced from 0.19 to 0.019. But the performance of third Java and third Python deteriorated 6.4 and 2.2 times when training of GIT respectively. When training of GIT, the numbers at the RSA level also changed, including short Hadoop. This was further confirmed the impact of GIT for the I-cache method. Putting pieces together, we conclude that having a high format and style is not the enhanced character of the scale-out workloads. We measure the injection max of OC and Java implementation workloads more 2015-6 and shorter at the 3 levels and compare their pairwise similarly. We have the following observation. First, the instruction characteristics similarly between two workloads. Implementation only the RSA and Microarchitecture levels do not guarantee the instruction behavior characteristics will be definitely similar. For example, Metamir Java and Sort C have high similar at both RSA and Microarchitecture level. Second, the similarly our instruction characteristics between two workloads at the IR level is not necessarily consistent with those at the other two levels. For example, SAR256C and Metamir C are similar at the IR level, but not similar at the RSA and Microarchitecture levels. Indeed, they are different. Metamir C has lots of fault-point operation, where SAR256C is integer operation intensive. Third, implementation of the same workloads calling a dynamic link library or directly implementing the function in the source code have significantly different workload at the IR level. For example, DR2C language application for SAR256, SAR256 SSL-C and SAR256C call an OpenSSL dynamic link library, where SAR256C directly implement SSHL in the source code. We notice the SAR215C and Sort C are similar, as their constant distance are less than 0.1 at 3 levels. In fact, SAR256 and source are similar in instruction mix, as they both have intensive data access and interoperation. As the previous benchmark subsetting work that aim to remove redundant workloads calculate metrics at only one level. We attract that AI inference workload based on WPC across intermediate representation, RSA, and Microarchitecture. Finally, the inference model. We have three inference models: server model, serverless model, offline model. And the server model is the online server model, quite proceeding coverage of an inference benchmark. The matrix is latency and tail latency. The serverless model is loading machine resource on damage. The metric is the server start time, memory consuming path, throughput. Finally, the offline model is based on processing a base inference process of an interface benchmark. The metric is interface time and interface quality. The conclusion, the AIBench Inference is AIBench Inference website is that it continues 19 respective AI tasks and models, and have a WPC method, and have 3 models. We have a demo on to introduce how to use AIBench Inference.